IMFs, the weakest of which is London dispersion forces. When you're thinking of these things, we've talked about different types of bonding already. Covalent, they're close together on the periodic table, they share electrons. Polar covalent, not so close together on the periodic table, they got a lopsided sharing. One gets the electron a little bit more than the other. We talked about ionic, give and take kind of bond. Okay, one gives up the electron, the other one takes it. We talked about metallic. Metallic has a positive metal ions, like the alloys, like we made with alchemist gold when we made our brass. And it has the electrons that, like I said earlier, go muck-a-muck in between them. They just sort of do whatever they want to. Okay, these are now, those forces that we talked about, those bonding, were between elements to make a compound. IMFs are between molecules that we've made, how those molecules interact with each other. Okay, so London dispersion forces happen with all compounds. Okay, it's sort of like you're in this classroom, so you have LDFs with the rest of this class. Even if you're not friends with them, you have LDFs. You have some kind of relationship with them. We don't know exactly what it is, but you have something. Okay, that's what an LDF is. Sort of like the London fog. It's there every morning, and then it's gone. It's there every morning, and it's gone. So an LDF can happen when we have like CH4. CH4 has the carbon, it has a hydrogen. If we draw it on a flat plane, it looks like this. But in 3D, it's actually that one that I built for you, and I tossed it up in the air, and it landed, and it looked the same every time I did it. Okay, so it basically looked like, here's my carbon. We had a hydrogen up, we had a hydrogen out, we had a hydrogen back into the plane, and we had a hydrogen coming out of the plane. So it was more 3D. Okay, if I look at that and I think in my head, okay, hydrogen usually takes a positive charge, right? When it's with carbon, though, it's really close, so that it won't be a total positive charge. We get what is a partial positive charge. Lost my positive there. And so carbon here takes a slight negative charge. So it pulls onto the electrons a little bit more than the hydrogen is giving them up. As I look at that model, I can see I cannot cut with one line that carbon away from the hydrogens. Yes, ma'am? What? This is a delta. It's just a funny little thing. This is a capital delta. That is a small case delta, or lowercase delta. Yes. So it's not a full charge. So they're too close together. They're too similar in electronegativities that they can't rip the electron off of the other one. So one can get it closer to them, but doesn't quite have enough strength to rip it all the way off. So it has a partial charge, not a full charge. Okay, these are LDFs. Okay, LDFs are any molecule and how it interacts with other molecules. Okay, they have some kind of attraction. We don't know exactly what it is. It's not a polar one, because we can see here, we can't cut it in half. We can't get a positive side and a negative side. Weakest form, for the most part. There are exceptions to the rules, we already know. Okay, so the second type is called dipole-dipole. And dipole-dipole, this is how I remember it. I think of the poles, north and south pole. They're opposite, right? Well, same thing with dipole-dipole. We're going to have a slightly positive side, and we're going to have a slightly negative side. It's not going to be a full charge. It's not going to be a full charge. So, for instance, if I take H2S, and I put sulfur in the center, then I know that I'm going to come here and bond a hydrogen. I'm going to come here and bond a hydrogen. From what we've learned up here, I know that hydrogens are basically slightly positive. In other words, they'll mostly give their electron up. But the sulfur to here doesn't quite have enough energy to rip it off. So sulfur here becomes a slight negative. Well, if I look at this molecule, I can take, and along that line, I can divide the poles, a positive side and a negative side. Okay, so this would be a dipole. So if I can draw a molecule and I can sort of separate the positive side from the negative side with a one straight line, not a curvy line, but a straight line, then I've got a dipole going on. Okay, if it has a dipole, it still has the LDFs. Okay, now the third type, and the last one we're going to talk about is called hydrogen bonding. Now this one, scientists right now are conversing about. Some say it is strong enough to be considered a real bond, like covalent, ionic, polar covalent. And others say it's not quite strong enough. It needs to be in it needs to be in the IMFs, intermolecular forces, instead of a true bond. So what does it have to do with? It has to do with nitrogen connecting to a hydrogen, oxygen connecting to a hydrogen, or fluorine connecting to a hydrogen. I remember it as NOF, and it is on the top row of the P, NOF. So let's take one we all know, water. So if I was to make water, I'd have two unshared pairs of electrons, an H and an H. Everybody okay with that? Okay, because it's an O directly connected to an H, I've got a hydrogen bond. I also can say, oh, this side is positive and this side is slightly negative, so I also have a dipole-dipole. Okay, it won't always be the case, yes. So when you're making your compounds, when you're putting your compounds together, the ones that would have a positive charge, like the metals, they'll have a slightly positive charge here. The ones that were the non-metals or the upper part of the P, those will be the negatives. They'll be the negative side. Okay, so when you would have normally done your charges. Okay, so now what happens with hydrogen bonding is if we put a whole bunch of these waters together, and I'm not going to draw all the, well, I guess I am. Okay, remember oxygen is negative. Hydrogen was slightly positive. So what's going to happen is another water is going to come in here and be attracted to this hydrogen. And it puts a little bit of a bond here, an attraction. It's almost a bond. Okay, and then another water will come in. And it'll be attracted here with its hydrogen coming off. And they keep bonding like this, okay? And its attraction right here is not really a bond, but sort of. Okay, it's sort of strong. Well, have you ever watched when you take liquid water and you freeze it, it grows, right? It swells. The reason why is because it's got to arrange all of these so that the positives are next to the negatives, or next to the positives, and next to the negatives. So they arrange each other and it actually expands out. We get air pockets in between. Okay, so that's what's going on with hydrogen bonding. That also helps with water tension, with the meniscus that we have with water that we don't have with anything else, like oil. Okay, questions? Okay, I'm done with that.